So I'm Robert Stuart-Smith from Kakuja, a practice I share with Roland Snooks. And I want to talk today a bit about the organisation of architectural matter. And one way to begin thinking about this is to look at precedent studies of existing buildings, things that architects do frequently, which is actually, in one way, you could look at it as an analysis where we try to extract the intent of the architect's design and constraints which are embodied within the matter itself. In this case, this is a study of circulation by Dick von Gammeren of chateaus in England. And various architects, you can actually see, just through analysing things like plans and sections, very different ideas of space, program, materiality, form, space. Christopher Alexander, in Notes on the Synthesis of Form, talked a lot about how one can diagram design constraints and how they form different hierarchies within our decisions as architects. And some of these things are more related to each other than other things. Kakuja has an interest in formative processes and how we can embed design intent as intrinsic to a process of formation. So we want to orchestrate architectural becomings rather than explicitly describe what an architecture result could be from the beginning. So one example maybe of this would be, say, the materials philosophy of Gilles Deleuze, or say in some of the operative models of Antoni Gaudi. In this example, what you have is a physical model used in which he can constrain any design decision he makes to operate within a certain physical domain where he has a good compression structure, because he can invert the model of the catenary and it forms an ideal hyperbolic curve. Similarly, Fra Otto worked with performative models, soap films to simulate often fabric structures. And once again, you can see that there's a one-to-one idea of an abstract material computation of a spatial and formal result that's trying to resolve a structural principle. Now, while this is a powerful thing to kind of embed constraints within a design process, it's also limited by the physicality of the model. Like a lot of what Thomas was showing earlier in terms of CFD analysis would be a very difficult thing to operate with on a soap film model. Computation, on the other hand, by people like Stephen Wolfram, this is an example of a one-dimensional cellular automata. You can see all the diagrams up the top. They actually have different rules that are playing out to create what is a very periodic array, or a very differentiated one, or a highly emergent one. So in this case here, you have a series of rules playing out in tandem, negotiating, in order to arise at a solution that is qualitatively different from the rules that are fed in the first place. A lot of architectural design is now done digitally, and it's done using different logical code structures, whether it's done through a 3D modeling program or a script or a parametric program. A lot of these procedures follow different linear arrangements of rules. In this case, you have a linear, a branching, and a recursion diagram. Or maybe this is an abstraction of a parametric model, where one operation relates to the next one. Kakuja tends to focus on self-organizational systems due to their systemic openness. So what you see here, it's a similar diagram, except that there are local relationships made between some elements. And it's through the collective association of these elements and their interrelationships that we arise at solutions. One example of this is if you look at birds, a flock of birds, where they're computing the space between them, and they're constantly in dialogue locally between each other bird. Craig Reynolds described how you could simulate that as an algorithm through 3 simple rules, so that regardless of what position 1 or 2 birds are in, just through a few simple rules you can arise at complex formations of flocking. Similar algorithmic logics exist in things like swarm assemblages, such as in ants, or in construction programming of, say, termites, where termites operate through communication of pheromones and self-organization between the termites themselves. Why this is interesting from a design perspective is it's task-orientated and event-orientated. This is a breakup of different ants in a colony and their roles, which change both over the lifetime of the ant and also in proximity to whether they're near food or another dead ant and things like that. So through this idea of self-organization, we're aiming to solve various architectural problems and design intent, and to create a complex architecture. And what I mean by a complex architecture, complexity carries many meanings. In this case here, you have a diagram of an eye by Richard Dawkins, and he discusses complexity as a complex system being something made up of many heterogeneous parts, something like the eye or a Boeing 747, and they're put together in a way that if they were put together in another way, they would not perform that function. So there is some higher level property or function coming out of the fact that these things are together. Edward Lorenz, one of the godfathers of chaos theory, has two other descriptions of complexity that serve us here. The diagram on the left is a strange attractor, which describes how, with a mathematical function, a small change in the initial conditions can actually radically change the overall result. And the image on the right is of snowdrift. And here it's the detail of the geometry itself and the positioning and relationships between things are highly complicated, and it would take an awful lot of dimensions to describe how to set that out to someone. Lorenz is most known though for his for the Lorenz attractor on the top left, and for these kind of his idea of chaos and complexity within weather systems, where you cannot predict the weather too far ahead in advance, but you have tendencies and characteristics or behaviors of weather that are highly predictable, even if the precise weather pattern is not. And so Kikuja, in writing algorithms, we write custom algorithms for all of our projects. We're looking for how to design not only the kind of pragmatic aspects of projects, but how to embed within design and formation of an architectural result characteristics and tendencies that are intrinsic to the way we make a project. And it's actually that becomes a lot of our focus, and also the way these things are interrelated and exist at multiple scales. So what this means is we're not so we're interested, say, in the proportionality between one element and another, because we're not trying to necessarily express canonical architectural parts in the same way. Maybe one example of this would be the butterfly wing, where in addition to pigmentation, color arises also through the organization of material itself. So that the organization of matter at a very small scale actually causes some of the color differences you start seeing at larger scales. Another example of this would be the glass sponge, which is made of 100% silica, and it gets its strength, although it's an incredibly fragile thing, purely through the way it organizes its material into particular arrangements, where you can see multiple scales of order. So some of our projects have attempted to deal with this in various tectonic ways. And in this case, to start off a tower project we were supposed to build in China a few years ago, we were looking at Farado's optimal path networks and trying to assign agency or autonomous decisions to nodes on curves, and how they could self-organize into a coherent network where structure would become, in this case, a concrete exoskeleton. It would become a redundant network. So there would be an excess of structure there, but in order to not only have structure, but deal with natural light and ornament and various other aspects that we were concerned about in the architectural project. The project was looking at the facade as not only the structural condition, but more like an Owen Hower screen, something that actually produced a series of indirect voids where you could get a certain amount of light in a building, but at the same time have a indirect aspect to it. And it's actually, aside from the little part down the bottom, most of it's actually relatively economical to construct, believe it or not, where you just have two void formers coming from either side. This idea of agency through curves, though, has been taken through a number of other projects where, in this case, this was a collaboration for the National Art Museum of China with Studio Shu-Pei. And Shu-Pei had already been in negotiations with a number of people in the Chinese government and had been convinced to do a massive building on a podium. So we basically, in the beginning of this collaboration, were given the task of designing an envelope around a series of gallery volumes for a building that was 300 meters long. So, so in that case, we were looking at how we could create atrium holes through topological manifolds that would provide light down to the podium below, and how we could start structuring a glazing system that could kind of break down this mass into more perceptible scales and movements of turbulence. So in this case, a series of agents are programmed through relationships in code to trace out a landscape and a mass. And the level of connectivity between these agents, once again, this is all through local decisions. So it's kind of like a parametric model in the sense one can control very precisely behavior, but at the same time, it's a behavior that's unpredictable. And so you learn through rewriting the code again and again. And in this case, this is like a glazing structure, not so efficient from a structural point of view, but quite related to the way the facade panels were working. In this way, you can, maybe it's difficult to see, but there's a whole lot of turbulence in there. That there's actually an organization of the facade that's different to the massing, but intrinsically related to it. And each panel is actually the same size and shape. It's just there's a degree of overlap that is varying between the panels. There's some other facade tests and some interior shots. I think it becomes more apparent in the landscape here, where you start to see how a very particular organization of tiles has different effects at different scales, and you can start to read the order of the way in which it's been organized through perceiving it at different distances. Some of this has been explored at the moment through some generative drawings that we're doing for an exhibition, where once again difference is happening through swarm behavior, and so geometry is actually a very simple thing, but it's actually through local associations between elements and their desire to connect to each other that you get difference. So this particular image reminds me a little bit of an Henri Michaud sketch, like where you see degrees of intensity almost as if it's drawn in ink. So in these previous examples, you see very much criteria for those projects that's internal to Kuja in a way, like to do with trying to express qualitative aspects of formation. In this project, it was a terminal for Air Baltic in Riga, Latvia. This was a collaboration with Bureau Happold, where we were trying to embed our agent-based design methodologies with their structural methodologies. And our attitude to the airport was that most airport terminals tend to privilege spending all their money and energy on a roof that only departure passengers experience. So what we wanted to do is emphasize the ceiling as the design driver of the project, allow departing passengers to ascend through the ceiling so they feel a bit like gods perhaps, and arrival passengers to also have a nice experience of the terminal. So there's voids as well to get light down to the arrivals level, and you have this very transparent facade where you have baggage reclaim and check-in, and then you ascend up to the retail. And you can see the transparency there. So the way this operated was to actually conceive of, first of all, designing the simple roof, and then allowing an agent-based negotiation to occur between the already desired spatial constraints and the formal desire of structure negotiating with architectural intent in regards to ornamentation. So what we have here is the diagram on the left is actually a reflected ceiling plan, and there's a zoom in there in the middle, and every dot is an autonomous agent. And I mean every dot has its own algorithmic rules that are coded, and it decides whether it connects or it breaks or makes a connection with an adjacent node. So the entire roof is structured in strands. And what happens is every frame or every second, this entire roof gets analyzed in a structural program, and each agent selfishly decides whether to make or break connections to improve its structural behavior. But each dot has no knowledge of the overall roof. So what happens is, over time, this simulation goes from being really fast to slowing down and settling. And at that point, it's pretty much resolved as best as it can its structural solution for the given conditions. And what happens is you get these three very local characteristics emerging that we could find all through the roof. One where you get a typical shell structure where it's just thinned out versus a kind of waffle slab-like conditions or trusses. But these are occurring just through local organization. They're not defined by us specifically or by Bureau Happold. So what you have in the result is not an optimal structure, and the desire was not to have it completely optimal. I mean, I'm sure you can look at this and know it's not an optimal structure, but it's a roof where the architectural design intent and structure are still intrinsic to each other, and structure is efficient for something that also has certain spatial, formal, and ornamental criteria. So a lot of these have been based on controlling curves in a way, and how one can embody algorithmic intent within curves. We've been thinking about morphology as well, like Darcy Thompson, and topology, the mathematics of topology, and how, for instance, this is Lewis Wolpert, a developmental biologist, how topology and morphology can be considered a complex series of events that occur in time that have a certain mathematics behind them, such as René talks about. This is an image by Stuart-Smith, very controversial in the scientific community, but interesting in the sense that it tries to describe, even if a bit naively, how one could generate any kind of vertebrate through a series of topological operations. I mean, it looks pretty off-putting when you see that, right? But what's interesting about it, he takes it down to every level of scale, all the way down to how to create feathers or fur, where he describes it as, say, a catastrophe in René Ton's sense, like where you can go from a surface being planar to folding to create a pocket where maybe a feather grows out of. And this idea of event-based behavior is something that he talks about, and also Goethe, also in terms of plants. But Wolpert talks about it in the sense that it's easier to describe a complex thing through its process of formation than to explicitly describe the result. And he gives the example of origami in the sense that it's easier to give someone the instructions for origami than to describe the geometry of an end piece. These are examples of Goethe showing the event-based rules of plants. For instance, here you're getting a flower growing inside a flower. And back here, like there's a transition between a leaf and these little leaves before you get to the petal. In terms of going back to our methodologies, these things are highly volatile. Like things can collapse or they can form a dynamic stability. In this case, you have nodes that have no physical connection to each other, but they're relating to each other. And although the result's always changing, there is a persistence of two spheres, one inside the other. To actually give design control, I don't know if you can see that actually very well. To actually give design control to these kinds of things, though, is difficult. For instance, in this case, there's an attempt at forming an overall surface formation through points in space, and you only see a result for a fleeting moment. Can you see that at all? Okay. So one way of controlling this was actually to embed knowledge of surface within a swarm system, to actually give it an understanding of topology and some abstract sense of materiality. So in this case, this is just a simple springs model, just basically looking at surface tension and how you could include that, and then how you can incorporate that within a swarm system. So in this case, there's not just surface tension, there's also each node is trying to negotiate its spatial relation to another node, so that they're constantly moving around each other. And although that might look a bit strange to you, it's in a very precise set of spatial positions where everything's maintaining a certain distance from itself. And you can also treat it a bit like fashion design and start to think of pattern making and how you can assemble things. So in this case, this surface actually wraps itself up into a very desirable configuration. Or topological change. Each color represents a different set of behaviors that have been encoded in this surface, so it actually understands if it's on an edge or a tube or anything like that, and it therefore makes different decisions about what to do. So this was first tested on an opera house competition, which was for Busan in Korea, and was looking at trying to use local ceramics and glass in order to create. I won't actually go into the design on this one. I'm more interested in talking about other things with you today. But basically it was taking this methodology, and before you just saw some abstract diagrams. In order to design a project on a site, it suddenly had to have a few constraints. And so in this case, this is actually the setup for the simulation, because one could simulate something from nothing, but at the same time, it needed like these anchoring positions in particular. And so this goes from that to that. And it's difficult when you watch a video of this because it looks very deterministic. But what I have to remind you is that it took 3,000 simulations to design this project, and during that time we were rewriting the code constantly, and it was the first time we'd used this particular code on a project, so it was still pretty rough and we couldn't actually add other criteria to it. But basically, what you see at the result, you see a gradient also in opacity. As you get towards the water, you get just glass, and then you go to frosted glass and then ceramic. But unlike, say, Luigi Colani, who gets, say, small details on a building through sculpting, what's quite interesting about this project is that the overall mass is emergent, and the local characteristics, like the little ridges of Luigi Colani or the collarbone-like qualities on the left, are actually also intrinsic to that mass. That one is not added later on. In fact, the overall formation of the whole building is actually mainly due to those local conditions. Because of a local pull or tensioning, the whole thing has kind of moved in on itself in order to form this. And as I said before, this process is a bit difficult to work with because you're constantly going backwards and forwards. Like in this case, it's difficult to train thousands of little dots to decide what building to form. You're still the architect. So this was constantly being simulated over a simple Rhino 3D massing model that we'd, determined where all the program was. But you get all these local characteristics that are quite intrinsic to the overall formation of the project. The auditorium was done the same way. So at the moment we're working on a project, I can't tell you too much about it, but it's taking that same methodology and thinking of it as something that tectonically could be done in timber and operate between three conditions within the one project, between post-tension compression, cable net suspension, and fabric-like drapery. Now, this is super rough, so don't think of this as final geometry, okay? But the idea is that in the center of this building, it forms an atrium, which it is then self-supporting, and then it actually turns in underneath a very simple timber box and becomes a suspended ceiling. And it's also pulled down. This is the ceiling itself and the outside surface of the atrium. So once again, it's an interest not in pure structural expression at all, but as in this desire for excess in a sense, like more like a Bernini sculpture or something. There's like a desire for folding and ripples and all this kind of thing at the same time as structural principles being embedded within it. So it's trying to fuse tectonics and design intent within one type of design methodology. And it's a little bit chunky at the moment, but it's made out of all flat pieces of laminated timber. But there's a continuity happening through the connections of the cables. And once again, this involves a lot of simulations, and you can, I think it's a bit difficult to see here, but there's actually some ridging and things on the ceiling as well, similar to what you saw in the previous project. So going from this kind of idea of formation in tectonics, I run a studio at the AA in the Design Research Laboratory, where we've been trying to add an environmental ethic to these kinds of principles. And so looking at ideas of waste, and also an understanding that often a lot of architectural advancement has happened in connection with changes in tectonic possibilities. So Frank Lloyd Wright's exploitation of cantilevers was made possible, for instance, because of structural steel and concrete. And how climate, social organizations, economic ones often follow cycles and have time periods, and how formation in nature also actually operates over time. So there's a few ways we've been looking at this. One is through temporality as a design driver. Another is fabrication as a generative possibility too. And another is through algorithmic placement of material pre-fabrication. In terms of temporality, we've been looking at things like how to control water flow over time in a building, so one can go from one route to another by simulating erosion. In this case, these students actually developed this is a 1 to 2 meter high prototype. They did material hardness tests and things and worked out how they could actually erode a building over time. And once they knew how long it would take with the right mixtures, then they could start to develop their own simulation tools. So once again, this is like heavily requiring them to take on a computational attitude to the way they organize material and starting to develop a relationship between geometry and erosion. This is a test where you can start to see actually some of the qualitative ornamental effects of erosion itself. That's a 1 to 5 model. And so they start working with that too. And perforation as a principle. So the idea of the project is that by controlling water flow, they're able to program a 1-year cycle where part of the building perforates for summer. It's a public bath. And another part of the building operates on a 10-year cycle. So part of the building's rebuilt every year. Another project has operated a similar way, looking at supple membranes and how by embedding hydrogel within a membrane through certain veins, they can actually program to redirect water once basically this membrane soaks up a certain amount of water, which changes the weight of the way the membrane sits, and then it redirects water to a different path location. Other projects have been more speculative, looking at how to use mycelia or mushrooms to actually build the building for the mushrooms itself. So the farm is a building. And in order to develop that, they were looking at how to grow mycelia and the fact that it binds to itself. Through a substrate, it grows in a hay. They were looking at a project in China where there's the most amount of rice hay waste in the world, and working out how much productivity they could get from this waste on a particular rice farm site. So their building size is based on what is wasted on the site and what they can produce from it. And also they're using a technique of forming these tubes, which is done a lot in agriculture in terms of binding the hay. So they're doing structural analysis to work out how to actually make this material support itself. And the way you organize it radically affects its structural properties. And then working out the cycle of rice to 3 cycles of mushrooms as well. So the building is actually built in stages, and the mushrooms are getting farmed in stages as well. And this building's built once a year. Also looking into acoustics and how to make acoustics a phenomenological property of architectural space and form, and how just slight manipulations in architectural space can change both the interior and the exterior sound effects of that one can experience. So that's an idea of temporality. In terms of fabrication we also see as an opportunity to be part of the creative process of design. So in this case, looking once again at waste, a lot of complex double curvature buildings use a lot of formwork. So these students of mine now have a patent on this actually, but The idea is that you basically have a very simple prefabricated, you have a box set up and you prefabricate concrete panels, but the idea is that the previous panel becomes the formwork for the next panel, and all you have to do is vary the amount of concrete you place in the corners, and it starts changing the depth and the configuration. So you start to see every panel being cast on top of the other one is different from the one before. And this is them testing this out and what kinds of things it can create. Even overlap conditions, it's quite precise, speculating on how they can use it. But it's easy for them to calculate how many pieces, how much material's used, and what kinds of things it can make. But what I think is quite interesting about it is that there are certain characteristics of it that are intrinsic to the way it's made. And although they can put in any mathematical function, they can also have all these stranger things come out that are just as easy to make as things that you would normally make. And so you can start to actually read some of the differences and the sequence of construction when you start to look at any patch of their project, because it's actually building itself in lines and you can start to read the continuity of the casting process. The last example I want to show you is to do with strategizing where to place material in a sense before you build it. And so this is a student project looking at 3D printed plastics and how, for instance, in a chainmail configuration, you can actually program how you can bend material in particular ways. So to create things like curtains. So in this case, you have a materiality that goes from rigid to supple within one print, and how to code the computer process itself. So in this case, they've hacked into the 3D printing machine to create things that doesn't normally make, like hair or fur, or kind of like delater, how do you say it? Like, you know, when you pull over a sweater starts to come apart. And building at their own topological structural optimization tool, so writing their own code to develop a way of minimizing how much material they need in order to perform a structural condition, but also looking at what it means spatially. In this case, this is a 2-story space, and they're saying that there are 2 ways they can optimize that material, and they have different implications on what space it creates. So they're thinking about the relationship between space and built material, and how that can be prefabricated, that 3D printing still offers a lot of opportunities in prefabrication, not just on site. And they were testing that on a cantilevered condition on a site, which had good reason for prefabrication. So it's broken into parts that are transportable in a truck, and each of these parts is optimized structurally initially. That's already topologically optimized, but then part to part is optimized, and they're able to extract all the stress lines of this and then strategize how to actually place material within the realms of the structure. So you can see here, you know, different lines of stress within the material, and then algorithms being written for material placement that respect the stress lines. And once again, it's trying to subvert the part-to-part relationship you see, say, in Maison Domino, and looking at the way material can be organized at smaller scales in order to arise at solutions that still solve an overall effect as a result. In this case, this is like a 1.5 meter long 3D printed model made out of 15 parts that each are organized with like less than 1 millimeter diameter strands. So in this case, it has a structural performance. It also has an excessive ornamental quality, you could argue. But it's actually highly porous. So it's actually extremely light and doesn't use much material, even though it looks like it uses an awful lot of material. So yeah, just on that note, what I'm arguing for with you today, or what I'm exploring, let's say, and what we're exploring in Kakuja, is an idea of organization as being a key design driver, and that you can actually start to organize materiality at smaller scales in order to generate effects that are qualitative beyond just the pragmatic aspects of architecture. So whether we're talking about efficiencies in terms of structure, or we're talking about more phenomenological or qualitative aspects that can give maybe a more humanist quality to architecture too, whether it's to do with temporality or aspects of buildings changing and our relationship to, say, a building cycle as something that's a design opportunity, not just an opportunity for rationalization. So, yeah, thank you.